And now it's time to take a look at the part of sensitivity analysis where we have had the corner point, which produces the optimal solution at the intersection of two of the lines from two of the constraints. And we want to know how much can the constant that one of those constraints is less than or equal to, how much can that shift by and still have the optimal solution be at the intersection of the two lines? Now, you were going to be shifting one of those lines. Okay, so remember that this is part of a playlist and it refers back to an original question. So I'm going to link that if you haven't viewed that. We found that the optimal solution was at the corner point produced by the intersection of x sub 1 plus 4x sub 2 equals 360 and 2x sub 1 plus x sub 2 equals 300. So I'm going to show by Gauss-Jordan elimination in just a moment how to find out what that corner point was, because that's not the method I used originally. And then we're going to take a look at shifting that first line. Adding h could be positive or negative. And so we're going to have things parallel to the original line. How much can we move that around by, keeping it parallel to the original line and still have it be at the intersection of these two constraints? So putting in equal signs and creating an augmented matrix. We've already got a 1 on the diagonal here. And so I want to get zeros in the rest of the column. I'm going to come up with a new row 2 by taking this as our pivot row, and specifically this is our pivot element. Multiply it by -2, and do that to all of row 1, and add it to row 2 to get a new row 2. And remember, you can use a TI-84. You're going to take -2 times row 1. We can get all of this to happen at once. -2 times row 1, opening with second and the opening square bracket above the multiplication sign. Got 1, comma 4, comma 360. Also notice that I had to use the negative symbol, not the minus symbol. Closing, second, and above the minus sign. Whoop. Plus our original row 2, which was 2, comma 1, comma 300. Close that up. Now that does mess up our one that was on this part of the diagonal, but we're going from left to right. So let's see here. All right, now we've got an unchanged row 1 and 0, -7, -420 for row 2. So I'm going to get a new row 2 from that, get a 1 on the diagonal since I've got my unit column in column 1, multiply everything by -1/7, i.e. dividing everything in row 2 by -7. now that I've got the one on the diagonal there in column 2, row 2, column 2, I'm going to give that 4 above it to be a 0 by creating new row 1, taking -4 times row 2 plus row 1 and get a new row 1. So how's that going to look? All right, here we go. -4 times, let me see if I can take that previous answer. Oh, well, I'd have to get that multiplied by the -1/7 as well. Let's see if that'll work. Did not. Oh, okay. It's giving me -4 multiplied to all of that. So add that to row 1. See if that part will work. Every once in a great while, I overestimate the shortcuts that I can use, but let's see if that works. It does. And so here is the row reduced matrix that we have, with the corner point being at 120,60. That's the same corner point that we found by a different approach earlier. So now what about this question of having that 360 plus h? Well, plus h. Then we would have had, besides the -720 plus 300 added to get -420, we would have had -720 minus 2h added to 300. And when we multiply everything in this new row 2 by -1/7 to get yet another new row 2, then besides the 60, distribute that -1/7 being multiplied to this. -1/7 times -2h would be 60 plus 2h. Oh, plus 2/7 h. And we've got 360 plus h here and here. And then finally, when we multiply everything in row 2 by -4 and add it to row 1 to get a new row 1, let's see here. -4 times 60, and continuing to distribute, -4 times plus 2/7 h would be minus 8/7 h. And so adding, going to have 120 minus 1/7 h. And so this would be our new intersection points when we're moving this around. Now, real quick, I'm going to double check that because I wrote this problem out previously, by a different method. And then after checking that, if I'm right, then I'm going to show this on GeoGebra. Okay, remember that we were maximizing the following function. Z equals 10x plus 15y if we replace x sub 1 with x and x sub 2 with y. All right. So in our original problem, we were sliding around the objective function here and finding a maximum was being caused at 120,60. And our maximal solution was, let's see here, 2100. All right. So backing it up a little bit. Well, jumping past it, but right around here, you can see the 2100. Okay, well, the H, what that's doing is, let me zoom out a little bit here. The line for the second regular constraint is not changing. We still have a x-intercept at 150, 0 and a y-intercept at 0, 300. As for the boundary line of the first regular constraint, it still has a y-intercept at 0, 90. Apparently I misspoke and we do not have something parallel to what we originally had. If we were to try to let these run at the same time, it would be difficult to keep track of both things moving and finding out the range of values that H could have, and therefore the range of values that 360 plus H could have. So we need to do a little bit more written work here. And you might wonder, well, how could we do that? Well, here it is. We had the non-negativity constraints. The x sub 1 and x sub 2 both had to be greater than or equal to 0. Both of these have to be greater than or equal to 0. So if I solve each of those inequalities, then I can multiply everything in the first one by a positive 7 and get 840 minus H still greater than or equal to 0. And in the second constraint, every term on both sides multiplied by positive 7, and that's going to give me 420 plus 2H greater than or equal to 0. So 840 has to be greater than or equal to H from the first one. And from the second one, let's see here. I could divide everything by 2, a positive 2, so that won't change the direction. 210 plus H from the first one. Subtract 210 from both sides and get that H has to be greater than or equal to negative 210. Looking at the smaller and the larger, and putting that, instead of saying H greater than or equal to negative 210, put it as negative 210 less than or equal to H. When you put it all together, then we have negative 210 less than or equal to H less than or equal to 840. And then when you consider that that was 360 plus H back up here. That's going to put the right-hand side of constraint 1, that regular constraint, 360 plus a negative 210, i.e. 360 minus 210 is 150, and 360 plus 840 is 1200. So it could be between 150 and 1200. Taking a look at that, negative 150 and 1200. Let's see here. $50 and 1200. Sorry, that's a positive 150 and 1200. And again, trying to look at both of these changing at the same time is going to make it difficult to tell for those different values of H when we're going to get the maximum value at point C still, the intersection of the boundary lines for constraint 1 and constraint 2. But again, we're having constraint 1, we could have x of 1 plus 4x sub 2 less than or equal to 150, up to x of 1 plus 4x sub 2 less than or equal to 1200, and still gets the intersection of that boundary line from constraint 1 with the intersection of the boundary line from constraint 2, and that would still produce the maximum.